which is part of the European Social Fund. So, before I continue, I was reminded by Thomas and Catherine as I wrote this talk that this is summing up 3 years' work in 20 minutes, which is quite an arduous task. And I was reminded of a great quote by Sigmund Freud about giving a presentation that nobody understood anything, but they thought he understood it, and that was all that really mattered. So I'm trying to emulate the opposite of it, and I have prepared. I haven't taken lots of cocaine to make this talk work. So, going through this automatic transitions. I don't know why it's doing that. Sorry. My project has 3 major kind of branches. Focus in particular on one of those. Because it's quite a short time constraint, but I'll give a brief overview of the other things I've done on this project. So the first aspect of this project is thermal modeling. So vitrification or freezing of oocytes and embryos is a really emergent process, and clinics are using it all the time because people want to preserve their fertility. But obviously when you subject an embryo to really, really low temperatures, you're putting it at risk of damage. And so the clinic came to us with questions about how we can optimize the way they do the vitrification and the way they keep these embryos and oocytes stored so that they minimize the risk of damage, but maximize the chance that this embryo is going to survive. And we've actually got a publication, which I guess Thomas has got on a mug, which is very nice, in cryobiology, looking at the different arrangements of these oocytes and embryos and how that affects the rate of vitrification, how it doesn't affect the rate of vitrification, so it's still okay to do in the clinic. I don't know why this is automatically transitioning. Very strange. But
is there another way to present rather than the kind of timed present?
I never put any times in it, so
yeah, just the bottom right present.
Yeah,
is that what you're on?
Yeah.
Oh, okay.
Oh, sorry to interrupt, guys, but maybe you could share your screen, Tim. I don't think it's running in the Zoom.
Share. How do you mean share? Oh. Yeah. Got it. Is that better?
Yeah, awesome.
You can minimize them. You can minimize them.
There we go. Yeah, cool. Looks like it's still doing it, but I'll just have to deal with that.
Yeah.
Okay, and then the third aspect of my project is differential dynamic microscopy, which is a technique that was introduced to us by my biological collaborator, Professor Carl Swan, and I'll go more into detail about that. So, what is differential dynamic microscopy? It's a technique that's used to derive motility parameters from underlying time-lapse image data. So for those that are interested, I'm going to give a very whirlwind tour of this, but in particular, this paper by Germain et al. Is really, really useful. It's got a nice data set, which is where I got this GIF of some colloids that are undergoing Brownian motion from. It also has source code, so anybody who's interested in the technique, I thoroughly recommend giving that a look. So the motivation behind this problem is we have this is some data that's given to us by Professor Swan from his lab. These are mouse oocytes. And it's kind of possibly hard to see because the motion is so small, but these are kind of jiggling and there's motion inside these eggs and oocytes. And there are papers such as the paper by Advection et al., which looks at characterizing the speed. It's called a basal speed, and relating it to the underlying metabolic health of the oocyte. So we're thinking the more it moves, the healthier it is. And looking at this and the DDM technique, we want to try and relate the basal speed in the eggs to something that we can characterize mathematically. We're looking at diffusion coefficients. So we're treating this as diffusive behavior. So this is a nice GIF of some pollen grains that are undergoing Brownian motion, which is a diffusive process. And we want to try and establish this equality, this link between these two things. If we can show that DDM can characterize the basal speed in these eggs, we can use it as a technique to characterize their metabolic health, which is a massive interest to an IVF clinic because it lets them select healthy eggs. So I'll give a whirlwind tour of what the DDM algorithm actually does. As I say, if you've got more questions or want more details, I do recommend this paper and I can suggest other papers as well. So you start with a movie, which is just a big tensor essentially, where you've got Cartesian coordinates, which denote the location within the frame, and time, which denotes at what time each frame is taken. So this is a prototype example where I have a movie which is only 4 frames long. I'm going to call that I. Next, when you're looking at motion, we want to know what's changed. So we're going to take the image differences. So for any 2 frames, we can take one and subtract another from it to tell us what's changed between those 2 frames. That gives us our image differences. We can characterize these based on how many frames we've actually moved to get that difference. So there's 3 different images that are separated by a pair of 1, 2 images that are separated by time lag of 2, etc. And we can explore all the differences as we go up those time lags. The next step is a bit of a jump, and that is taking the 2D spatial Fourier transform of each of these stacks and then taking a time average. So we don't necessarily care what has moved in each part of the frame, we care at what frequency they're moving, because that helps us to generalize the behavior across this entire structure. So we take the 2D Fourier transform, and then we do the time average, because we expect the behavior to remain the same at each time step. It only really depends on the time lag. And then finally, we take a radial average, and I'll explore the time average and the radial average in a second, but that essentially gives us this Cdn matrix, as it's called, where we've got parameters of spatial frequency magnitude and time lag of delta t. And each entry in this matrix should tell us what has changed at a specific frequency magnitude and time lag. And with the time average, it's just adding together all of these image differences after the Fourier transform that have the same time lag and dividing by the number of frames. And the radial average involves drawing a circle that's centered at the center of the frame and averaging over all the pixels that circle touches. And the reason we might want to do that is because it's a massive dimensional reduction, and it, take a massive image stack that's got loads of frames, really high resolution, we can condense it down into just a very small matrix.
Hi, Tim, sorry to interrupt again, but the Zoom share screen is frozen. We can only see 1 slide. Maybe you need to switch to the other monitor.
Okay, let me just... Is that any better? No, you can just see the...
Yeah, we can see the slides now. There's some overlay on it, but it's definitely before.
I don't know why it's been working so well. But...
Maybe you could mirror your display rather than.
Yeah, I don't know how to enable that actually. It's just because I've got the HDMI cable plugged in that's doing it. It wasn't doing it earlier.
Yeah.
Yeah, awesome. It works.
Is the wrong? Okay.
We can see the slide now.
Yeah, I just got to backtrack it.
Sorry about interrupting, by the way.
That's fine. Otherwise, I would never know. So thanks for that. So the reason we might want to do that entire process is we've got this Cdn matrix, and using a bit of complex number manipulation, we can rewrite it in terms of this structure here, where we've got something that depends on the frequency magnitude and the time, and we've averaged over time, which is what these angled brackets means. So that just depends on the spatial frequency magnitude. So we can just call that some term A. We don't really necessarily care what it is, we just care that it's there. It's a scaling term. We also have this B term, which is just added in. It doesn't come from the previous line, but it's added in because it accounts for noise within images. Whenever you take microscope images, there's always going to be noise and you have to account for it. Then finally, we have this structure, which we're going to call F. And in literature, this is called the intermediate scattering function. And we can actually show that it's just the same as taking the real part, the Fourier transform, of the probability distribution of the underlying displacement. So it's a bit of a jump, but this comes from the study of Van Hove functions, and it's just something that's established in literature. And it's all to do with essentially the autocorrelation of these underlying processes and how the position of one object will change over time. So a nice way to show this is with an example. We're going to treat Brownian motion. So Brownian motion, work by Einstein and many other people, has shown that we can essentially show how Brownian motion works by solving the diffusion equation. So take a diffusion equation with the initial condition that particles have no displacement at time 0, so they start at their initial location. And if we solve that, we can get this nice normal distribution, which we plotted here a few different times, that shows us essentially the probability of the single particle displacing by a certain amount at a given time. If we Fourier transform that and take the real part, it's actually already real valued, so we don't even need to do that. And we get the intermediate scattering function. It's just the exponential of minus q squared d delta t. So we have an analytic form for this F. If we numerically derive the DDN matrix, we now have an analytic expression for how it should look, and we can just run some non-linear least squared curve fitting to pull out this diffusion coefficient d. So we've now got a way of pulling out these parameters from these underlying terms. And this is already established in literature. There's also a couple more nice results that we can show that aren't really touched on, but if you have the sum of two independent processes and you want to know the intermediate scattering function of the sum of those processes, you can just multiply the individual intermediate scattering functions, and that's a consequence of the convolution theorem. And also, if you have a family of n particles, so say you've got a frame in which there's two different kinds of particles that do two different kinds of things. If you have the weights, which are just a percentage of each particle, so half of the particles are in family A, half are in family B, you can take the weighted average of the probability density functions, and then that just gives you the intermediate scattering function of the whole frame is the weighted average of their individual intermediate scattering functions as a consequence of the linearity of Fourier transform. So, for example, Advection diffusion dynamics, which is something else that we've studied a lot in this particular field. You take the Advection diffusion equation, same initial condition, and the intermediate scattering function you get is this diffusive part we've already seen before, plus some advection term, which here is just a cos function. So where we come into this problem is we already have the technique, we ran it on some eggs, and we noticed a few problems that people might occur. And we want to know, is DDM still valid when some of its core assumptions are violated? So looking at the egg data, we noticed two things. DDM relies on ergodicity, which means that essentially one particle will visit any part of the system, or alternatively that you take one particle and that will represent the entire species. And isotropy, which means that there's no bias in the direction of motion. The particle doesn't care which direction it moves, it will pick randomly essentially. And eggs actually violate both of these conditions in two ways. So here we have the eggs, and we can see they have clear boundaries. If I'm studying particles at the boundary of the eggs, they're going to bounce off the edges, they're going to interact with the edges. Also, we violate the isotropy, and I'm just going to quickly replay that flip. Okay. You can see there's some cytoplasmic streaming going on, so there's a directed motion. So it violates both of these conditions. And we're able to show that essentially, I won't go too much into these results, but we can get around this ergodicity problem by just simulating our intermediate scattering functions. So we can generate these more complex probability density functions. This is just on a line using the method of images. And by doing that, we can generate these intermediate scattering functions without needing them analytically and just numerically match them. And it works quite well. And we can also deal with the isotropy by, instead of taking the radial average, we can just look at these directions of motion. We can study the surface rather than a single curve. And we can actually pull out these results quite nicely. We've also explored with Advection diffusion dynamics, the effect of the Peclet number on the system and how accurate DDM is, because at the moment there's no real guidelines on how to make DDM work well. It will always spit out a number. I once ran it on the opening 10 seconds of Never Gonna Give You Up by Rick Astley, and it gives you a diffusion coefficient with no real guidance that you shouldn't have done that. So a lot of the work we've done is trying to give guidelines for users on how this technique should be used properly. And so we can actually outline regions of the Peclet number in which this technique is more or less accurate. But in particular, I want to touch, I don't have too long to do it because of all the tech issues, but we want to describe, this is a piece of data we were given by our biological collaborator and also in collaboration with the physics department. This is a differential interference contrast image of an egg, and you can see it's quite shadowed. Bottom left corner is dark and top right corner is bright. If you look at individual features on the surface, that shadowing is also present. It's an inherent feature of DIC. And we wondered if this affects DDM, and we looked at these. These are parts of the DDM matrix before the radial average. You take a single time lag, and before the radial average, you just study the surface. This is in bright field imaging on colloids, and you can see it's nice and circular around the center. It's got isotropy. This, however, has a massive directionality to it, and that aligns with the shear direction. That's when you do DIC images on also colloids, which we know are isotropic. So there's this artificial anisotropy that's been introduced, and we don't know if it affects DDM or not. So in order to understand the effects of DIC, we need to understand how a DIC image works, but that's quite complicated. You know, there's lots of lenses and lots of prisms. Trying to characterize this mathematically is a challenge, but nice literature search gives us this relation. So if you let X be some bright field or phase image, just a normal image, you can write DIC image I as a difference between X and a shifted version of X. So you shift X by a tiny amount, and that's your DIC shear, subtract one from the other, and it gives you your DIC image. So I've simulated here some particles in an image X, and this is what the DIC image would look like in that case. You can see that shadowing, it's brighter on the left and darker on the right. Now, doing the same thing that we did with the original DDN matrix, we've now got the DDN matrix, or tensor in this case, of the DIC image. And we can express this using some complex number manipulation in terms of the DDN matrix on the original image, plus some term or minus some terms that have to do with correlation between one image stack X and one image stack Y. So using a couple of facts that we know about image registration problems and autocorrelation, which is just coming from the original DDM, we can start dealing with these terms by making these Y terms, these X terms equivalent to each other and getting some relations out of that. And we come up with this key result, which is this Cdn matrix for the DIC image. You can express it as a scaling term times 1 minus cos qx0, where x0 is the DIC shear and q is the spatial frequency vector, multiplied by this 1 minus f. If we radial average that, nothing on here depends on the orientation of q except this cos function, which means the only thing we get left over is this 1 minus Bessel function. And because none of this depends on time, we can just rewrite this as a new scaling term and we get the original expression for the DDM matrix. So as we've shown here in this nice curve, we can actually run normal DDM without accounting for the fact that it's a DIC image on DIC images. We can then run it on the original image stack and multiply it by this Bessel function, and we get a perfect agreement, which shows us that actually, even though we get all that artificial anisotropy, DDM can still be used without any further consideration as long as the underlying motion is isotropic, which is a really powerful result because no matter what motion you have, as long as it's isotropic, you can throw DDM at it with DIC images. I don't have too much time to touch on it, but I'll briefly show. We also looked at advection and diffusion dynamics, so we've also given each of these particles a velocity with an aligned direction, and the DIC shear acts in another direction, and the angle between them is phi. And this gives us a much more complex expression for the DIC DDM matrix, which depends on all of these Bessel functions. And this is quite hard to study because as you get really small DIC shears, the functions are very tightly constrained by one and some lower bound, which is about 1 minus epsilon. As you increase the DIC shear, the behavior starts getting more and more complicated to understand. But with DIC images, we actually have the case that we have a very small DIC shear, x0 is small. So we can do some Taylor expansions around that term V, which is equal to Q times the DIC shear. So we can Taylor expand around that being small and get some different expressions for this mixed term to try and make things more simple. We have this left-hand one, this right-hand one, even though the left-hand side is a more accurate expression because it goes all the way up to order B4. The one on the right-hand side is actually a more robust fit. That's identified a couple of avenues for further work, understanding why this is such a good fit and why running DDM for this approximation gives us such good results. And partly we think that's to do with essentially comparing this H function with the approximation. They're very bad approximations, but they oscillate with the same frequency. And if you try and vary the velocity, so we have this term V over line, which is essentially the ratio of the correct velocity to the velocity we think is correct. And actually, when you look at the residuals on this fit, just varying that ratio, you get this global minimum when V is equal to 1, which means that even if we run DDM with this approximation, we're still getting the right results. So we need to understand what the radius of conversion is for this approximation so that we can have a good idea of when this is a good approximation to make. And we can even make it stronger and understand what parameter field do we need to be in for this approximation to still give us a good answer, even when the approximation itself doesn't hold. That is me done. I've run a little bit because of the technical issues, I'm afraid, but thank you to my supervisors, Catherine, Johnson, Carl, and also to my industrial collaborators, Giles, Helen, and Andrew. And I won't be able to hang around afterwards for questions because I have teaching at 3, but please feel free to send me an email or follow me on Twitter or come and ask my office.
Yeah, thanks a lot, Tim. That was really excellent. Have we got any questions in person, or I guess we can also take them from online? Maybe we start with any in-person questions for Tim. So we have no in-person questions to start with. Let's see if there's any in the chat or anyone wants to speak up online. I think we just had in the chat.
Obviously technical issues.
Yeah, people saying it looks perfect now, which is great. So it seems like a lot of the stuff came across nicely. I guess I just had the question. So what can you remind me quickly what DIC is?
DIC is differential interference contrast. It's the type of microscopy image, and they like it because it's really high resolution. You can see a lot on the surface of an egg, but it gives you that strange shadow cast effect when you use it.
But that generates your images to start with.
That's what you use to generate the images. And so we're adapting this technique to essentially account for all of these underlying things and still give you the right parameters. You're still imaging the same thing, but you're using a different technique.
Excellent. And have you thought about comparing your results here with some other methods? Like, I mean, I've used PIV.
PIV, yeah, particle image velocimetry, and
then you could actually say, well, this is the actual velocity field.
Yeah.
Does the diffusive properties of this agree with this prediction? Yeah.
So I actually used that when I was looking at I mentioned the Peckway numbers here. That's what we use as a ground truth. So we ran these simulations. So we simulated data, we ran them and used DDM to try and pull out the diffusion coefficient and the velocity. And we compared the velocity bits to what PIV would have said.
Okay.
So that we can make a good comparison and we can actually identify regions in which PIV is better for getting the velocity or worse for getting velocity than using this technique. And it's to do with kind of interplay between how noisy your fits are because of the diffusion coefficient and how strong the velocity field is.
Yeah, I guess it's the difference between the Fourier transform and like PIV uses like a spatial convolution, doesn't it?
Yeah, it does.
Just like the difference in how that follows through.
Yeah, and PIV also gives you more, this is kind of more broad information of the whole image, whereas PIV can give you more specific local kind of gradients. So there are advantages to using PIV.
That's a convolution in time, whereas yours is a convolution in space.
Yeah.
Is then time averaged. Yeah.
Yeah, exactly. And the advantage of using this in an actual clinic would be, ideally, you could just hopefully run this over an entire egg and it would just spit out a number at you. So it'd be very easy for somebody to use. Whereas with PIV, there's quite a lot of tuning that you sometimes have to do in terms of your interrogation window sizes, and hopefully this should be easier to use.
Yeah, no, that sounds very nice. I'm interested to use this technique in another context. That'd be really cool. Okay, so if we don't have any more, we've got one question on here. Wouldn't a WKB like approximation be better?
WKB, not familiar with the term.
This is kind of a Taylor series.
Oh, okay. Yeah, it was something that we should try. As I say, these approximations they're not particularly good approximations, but they still give us reasonable results. The advantage of making that incredibly simple approximation over here on the right-hand side is that if this approximation holds, you can actually do exactly what we did with the isotropic DDM and DIC and rewrite the entire thing as a scaling term multiplied by your original Cdn matrix. So under that particular circumstance, the previous result also holds for anisotropic behavior, but yeah, it's something I'd have to look at.
Okay. So yeah, if we don't have any more questions in person or online, so thank Tim again.